Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about iterative schemes. There's actually just a brief review. We already talked about it in a previous video in my scientific computing series. So yeah, we're just gonna review like all of the iterative methods, such as let's take a brief recap actually of what we talked about during that time. So we talked about this idea of starting with some initial guess, and from there we iterate. So we do something again and again until it converges to a solution, right? And so one of the methods that we talked about was the Jacobi iteration scheme. And we can use this Jacobi scheme using we can apply it to any linear system, right? And so here we're given a linear system. We start with some initial guess. This is random. And then we converge to that solution. So as we go, we arrive at a particular solution. And another thing, where was it? Is it doesn't guarantee that it always converges, right? So at some points, it will diverge. Let's say if we're given this linear system. So I'm pretty sure what we did here was we swapped those two, right? From here, we swapped these two, the first and last equations, right? And from there, where was I? And from there, if we try to solve it using our Jacobi scheme, well, we'll get a divergent solution. So we won't be able to find values for anything. What else? Yes, so we can solve this iteratively, and if it fails, it goes to infinity, whether that's positive or negative infinity. And so we talked about this idea of a matrix being strictly diagonally dominant, right? And what does that mean again? Well, it means that for each row, the sum of the absolute values of the off diagonal terms is less than the absolute value of the diagonal term. So this is the absolute value of the diagonal term, and it should be greater than the sum of absolute values of off diagonal terms. And if it is, then it's strictly diagonal dominant, right? Yeah, also, yeah, so the vertical lines mean absolute value. The KK means indices, KJ is indices. N is all the way. So we're going until we reach this capital N. This is a summation, sigma symbol. J starts at 1, and J can never be K because here we're considering only the off diagonal terms. And we're summing all of those up, right? And so, okay, if it is diagonally dominant, then it always converges to a unique solution. So it always converges if it's diagonally dominant. Um, and here is one of them, right? These are the diagonals. And we're going to determine whether the sum of the off diagonal terms is less than the absolute value of the diagonal. And so it is here, so it's guaranteed to converge. What else? Yeah, so we also have another method, which is the Gauss-Seidel, if I'm pronouncing it correctly. And this is basically a modification of the Jacobi iteration scheme. Because here, instead of just considering for k, well, we actually also do k plus 1. And what's the idea here? What's the purpose of this? Well, it converges to a solution faster. So here it converges to a solution in half the number of iterations used by Jacobi. So in other words, it's just more faster, right? But then again, it follows the same idea of strictly diagonal dominant. So yeah. Okay, let's talk about iterative schemes. Um, so last time, or in a previous video, we talked about this idea of direct methods, right? We talked about direct methods. And what are these? Well, say we're given a linear system. We're given a linear system AX equals B. And what happens here? Well, we solve for X, which means we just get the inverse of matrix A times vector B, right? And from there, what do we do? Well, we say if A is LU, so we decompose A into a lower and upper triangular matrix. Then we get LUX equals B. And from here, we say Ly equals B and UX equals Y. So we did talk about direct methods here. And so now we have a coupled system, these two. And basically for here, what do we do? Well, we solve for Y here. And here we solve for X. And why do we again do this? Because this takes O of N squared. So the whole thing takes O of N squared if we decompose it, right? We did talk about that. But if we did not decompose it, it would take ON cubed, which is much, much slower. So yeah, if we're given a linear system like this, it's usually better to use decomposition in some way, shape, or form. It's way more efficient. Okay, let's go into iterative methods here. So for iterative methods, well, the idea is that we guess. We make some guess, right? Let's say X naught. And then from there, we iteratively make better guesses, right? So from an initial guess, we get some sort of, I don't know, a set of numbers or a set of solutions. And then we go again and again until we make better guesses and until we converge to some solution, right? So let's do this in general because we talked about a numeric example before. So in general, let me do, okay, let me do this. So let's say I'm given a linear system at A11 x1 plus A12, and I think this is, oh no, this is x, my bad. This is y, A13z is equal to some b1. I'll not write it like that. B1. So here we're just making it as general as we can. Well, technically it's still not yet general, but we'll get to there. And 3, 1, x, 3, 2, y, 3, 3, z. And this is, well, what we call a linear system, but it goes all the way to 3. Um, okay, and this is actually the same thing as a of x equals b, where x and b are vectors, a is a matrix. Now let's make it general. I could isolate for x, y, and z for all of them, right? So let me do that real quick. So I'm gonna say here, if I isolate x from this alone, I'm going to isolate x. Well, I should get x equals, I'm assuming that's b. I subtract it to some value, a1 to y, and I add that to a1 3z. And this is over a1 1, right? Let me do y. For y, I get, uh, oh, this one's b1, and this one's b2, minus a21x, and I add that to a23z. And then I compute over a22. And lastly, my z, I'm gonna do b3 minus a31 x, assuming it's an x plus a32 y. I'm gonna do it over a33. There we go. Now we were able to isolate x, y, and z. And from there, let me make an initial guess, right? So I'm gonna say, given an initial guess, right? So we have an initial guess. We're going to fill it in the right-hand side and get a new guess. So the right-hand side, and we're going to get a new guess. So what do I mean? If we fill in an x naught, y naught, and z naught, then we should get a new guess, which is x1, y1, z1. If we fill in x1, y1, z1, we should get x2, y2, z2. If we fill in x2, y2, z2, we should get x3, y3, z3. So we're getting better and better and better. So what's the idea? In general, if we fill in xj, we get xj plus 1, yj, we get yj plus 1, zj, we get zj plus 1, right? So that's the idea. Until we finally get to a solution. So let me do that real quick. Okay. So here, I'm gonna do the formula. So the idea actually here is to use what we already have here. We're going to use this. Don't know why I'm taking a screenshot. Okay, let's use this. I'm going to, okay, no, I can't seem to. There we go. Oh, let me do this. Oh, that's what I was doing. Okay, I get it. Okay, let me just, there we go. I don't know why it always goes there. It's so weird. Oh, I can't use my, I did not mean to do that. Okay, let me just go here. Okay, there we go. Um, so what we're gonna do instead is instead of just x, we're gonna add +1. These are j's, yj, zj, xj, zj, y is j plus 1. So that's what we're doing here. We're basically getting better and better solutions as we solve this system, or as we start from some initial guess. Okay? So that's what's happening here. Now, let me just do this. Here we're saying that xj, yj, zj, what are these? Well, these are the jth iterations. I don't know what that is. Could be 0, could be 1, could be 2. And so from here, given, let's say, our initial guess, let's assume that to be x naught, y naught, z naught. This begs us the question, does it converge? Right? So what does that mean? It's either does the limit exist? So does the limit as j approaches 0 for xj, yj, zj exist? If it does, then it converges. Or it doesn't exist, meaning as xj goes to x, as yj goes to y, as zj goes to z, and as j goes to infinity, whether that's positive or negative. I mean, because we could be going, let me just make this precise, right? So these are questions that we want to answer. Okay, so here let's consider, so we let our vector x sub j. So this is a vector. It has xj, yj, zj, right? And then we also have a tilde. I still don't know what tilde means, to be honest. But here it's a matrix in this case. Okay. B. B over. I think they got this from the general. I'm gonna assume it's the general. Oh, they got it from here. Yeah. Okay. Here will we, what do we do? We have a matrix. And this matrix has, okay, we have 0, A12 over A11, A13, A11, A21, A22, 0, A23 over A22. What else do we have? A13, A33, A23, A33. So here you notice that the diagonal is all zeros, while the others contain elements, right? That's my A tilde. My B tilde, on the other hand, well, my B tilde is just going to be B1 over A11, B2 over A22. Yeah, it's really hard working with general stuff. And then B3 is A33, right? How did I get this actually? Well, I have my xj, yj, and zj, right? I multiply it to this A matrix. These become 0, and this B came from this one. B3 over A32, B2 over A22, B1 over A11, right? In my x iteration, my x is 0. In my first row, this one is 0. My second row, the middle one is 0. And my third row, the last column is 0, right? So this is just us translating this one from here. If I'm not mistaken, yeah. It should just be that. Okay. So we translated that in a very general way. Um, okay. I'm trying to look at the notes. Okay, so if we have those matrices or matrix and vectors, then what can we say? Well, we can say that our x vector, j plus 1, xj plus 1 is, well, b tilde plus a tilde xj, right? So my, hmm, yeah, so apparently if I do this, let me try one of them actually. Let me do the first one. Uh, this one becomes b1 over a11. I add that to this thing, axj. Yeah, a1 was my xj. So this a12 over a11 yj, and this one's zj, right? So this one, a and x, are basically these ones. Is that the same? Oh, it is the same. Yeah, 1, 2, 1, 1, 1, 3, 1, 1. 1, 2, 1, 1, 1, 3, 1. Yeah. So that's where they got the formula. I just tested it out to see if it works. Okay, so what they did was they converted it into matrices and vectors, this general formula. And then from there, they managed to derive this. And then I checked it. Well, we checked it for ourselves and we see that, oh, it is indeed equal to these three systems, right? These three linear equations. Okay, I can't even tell they're linear. Um, I would say they do look linear. If not, you can correct me. Okay, so what is this now? What is xj? Well, that is b tilde plus a tilde times b tilde plus a tilde x j minus 1, right? And then we go on and on and on and on and on. So another thing is, I don't know, we can go on and on. B tilde plus a tilde times b tilde plus a tilde times b tilde plus a tilde xj minus 2. I'm gonna be honest, I have no idea how many of these did we use. Okay. And from there, what can we observe? We see a pattern. right? J minus 1, J minus 2. So actually, this is just, what can we notice? Well, this is actually just equal to the identity matrix plus A tilde plus A tilde squared. Okay, I'm not sure how my teacher derived this whole thing. That was crazy though, because he was able to do it. B tilde plus A tilde cube xj minus 2, right? And then from there, he can now write a summation just to shorten things out. So this goes summation all the way to j, uh, L is 0. This is A tilde L. And then I'm going to multiply that to B tilde, which is equal to A tilde J plus 1. And that's my initial point x naught. So he was able to derive all of that, right? Still curious though, how did he get the identity matrix? Let me see. This becomes, mm, I mean, yeah, it's just, yeah, this is A squared, A tilde squared. This is AB. This is, yeah, it's just, yeah, so he was just able to do that. So basically what he did was he multiplied this to this to this, and then this to this, then this to this. Um, and then from there, you would multiply however how many those stuff are. So that's the idea, right? The idea is okay. The idea is there. Okay. Let me do converging. So here we're gonna say that the method indeed converges. How so? If my A tilde of J plus 1, right? Wait, I want to see where he got that stuff. I'm also a bit curious on the math behind cube. Well, that makes sense because you're multiplying A tilde, and A tilde. So that means A tilde cubed. So that makes sense. The A squared came from somewhere else, and this A thing is also weird. Then you multiply them all by this B. And then an identity matrix, so I'm assuming you multiply something by its inverse. That's how you know you get an identity matrix. Anyways, I'm not gonna go deep into the math now. I'll do it later. Okay, so to continue the lesson. Yeah, so the condition is that this will converge if my A tilde, J plus 1, as well as my summation of my L starting from 0, going all the way to L, or going all the way to J, I mean, A tilde L, if both of these converge. That means their limit is not infinity. So here's another thing. Actually, if my summation converges, so if this thing converges, then it is pretty certain that my A till j plus 1 definitely converged, right? Okay. Let me think. Now we're talking about series, which I not a big fan. Okay. I'm not gonna talk about series. I'm hoping there's another way. But yeah, that's the idea. If my summation converges, then my solutions would have also converged. Um, okay, but we okay. Mm, 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 mm. I'm thinking of how I'm gonna go about this lesson because this is a bit proof based. Okay, let me just go through some of them. I'm not gonna go through the geometric series, but the idea is that again, if this summation converges as my uh, a tilde goes to that j value, well, then my j plus one means my j plus one also converged. That's what it means. Um, okay. Let me actually look at what the geometric series is before I. Let's just a review. What is that? So there's a difference between geometric series and sequence. Let me just. Okay, I'm just gonna go to Wikipedia. It doesn't matter. Okay. Why is calculus here? What? Um, so there's an infinite series and a finite series. Okay. Uh, cool. Oh, and they converge to some value if we get their limit. That's interesting. Okay, actually, I know I don't need to review it. Okay, so if we think about, I'm just gonna go for it. Uh, let's say my geometric series, and this is a summation going all the way to n, starting from zero, l equals zero, my a to the power of l, and then here we say my a is a real number, could be any. Um, then this would converge. So a geometric series converges when the absolute value of my real number is less than. When I said real number, I literally wrote r. When my absolute value is less than 1. Okay. I might do like a supplementary video on this, but it doesn't matter for now. If you guys know geometric series, then that's really good because that's what he did as an example. Similarly, um, let's do a summation here. L starts at 0. So my A tilde, so near, here and now I'm talking about my A tilde. It will converge, just like a geometric series, when my norm, so here I talk something about norm. My norm of A tilde is less than 1. What do I mean by norm? Uh, okay, we actually call this a matrix norm. So it's the norm of a matrix. What does a norm mean? I don't know. I'm gonna Google it. What's a matrix norm? Even a Euclidean norm, that's a thing. Okay. Yeah, what does the norm tell us? A magnitude of a vector. No, obviously. It's basically like an absolute value. So here it's kind of like the magnitude of a matrix. Okay. So kind of like a magnitude. And so if you did go to my calculus series, it's kind of like a magnitude or length or stuff like that. Or absolute value. Um I'm gonna have to I'm not gonna go in depth here because we actually didn't go in depth in this case. Um Maybe in the next course that I'm gonna be taking, I will go in depth about norms and matrix norms. I also don't know it as of now. But yeah, the idea is it will converge. Um, okay, yeah, this is really just proof heavy. I would say this is really proof heavy. They prove it using geometric series and stuff like that and summations. Um, okay, okay. Let me just go through two more things. So we did talk about how iterative schemes will converge if A is diagonally dominant. Um, so here's the thing. This will not always converge, but we can think of other schemes, right? Um, okay, there's like a proof based here. Okay, I'm not gonna go through that. Okay, okay, I'm gonna end with this. Here's the thing. So just to end it off, we're just gonna talk about iterative schemes will converge if the matrix, so if A is diagonally dominant. And we did talk about it in a recap. So, okay, here honestly, any matrix, as long as it's diagonally dominant, we should be good to go, right? So that means, okay, so what's this notation? AII. So the absolute value of the diagonal element should be greater than the summation of, I don't know, of n. Doesn't really matter. Um, J is 1, but J should not be I, IJ. Yeah, so that's the idea. Um, the sum of all of the off diagonal elements in that particular row should be less than the absolute value of, well, my diagonal element. And from there, we can determine that we'll be able to solve it converge. We'll be able to solve a system of linear equations using this if the matrix is diagonally dominant. So yeah, that's it for this video. I hope you guys enjoyed. I hope you learned a lot. Um, yeah, I'll see you all in the next one.